Hello, today I'd like to talk about some methods for bounding calculation errors for linear systems. So I'm going to discuss two ways to bound the error on ax minus b that corresponds with the linear system equation, the typical one, ax equals b. I'm going to talk about Griffith's method. I don't know what else to call it, but it's based on a floating point round-off technique. And then there's a submultiplicative method that's based on matrix and vector norms. Pretty excited about that one. So bounding ax minus b. So let's take our very comfortable 3 by 3 example and write the errors as e sub I. So if you take your A matrix and your x column and your b column and you do the a times x and you subtract off the b, when you do that, you get a very easily recognized result, and we can call each of these rows E1, E2, and E3. So if you're given A and you're given B, and you have some idea of an X, so the idea is that you want these E's to be 0, and that would mean that the proposed x's, yea verily, are good solutions to the linear system. And when you do this in floating point, things aren't going to be always 0. Your true value might be 0, and that's what we think about, our true values of E1, E2, and E3 being 0. But the floating point representation from doing these calculations, they won't necessarily be exactly 0. And what we do is we set a bound for those floating point calculations. We say that the absolute value, for example, of E1, when it's calculated, the absolute value of that needs to be less than or equal to this 1. And 1 comes about from a particular factor times the machine epsilon. And that particular factor comes about from x1 times a11, that scaled by 4, x2 times a12, that scaled by 4, x3 times a13, that one scaled by 3, and then you're adding in the absolute value of b1. These are absolute valued, so this will always be a positive, potentially 0, but a positive value right there, and you basically replicate, index the row of the A's and the B in order to get your E2 and E3. So it's a very, very simple thing to get your 2 and your 3 squared away. And what I noticed is, boy, that almost looks like a matrix multiplication. It's just that we kind of have that pesky 3 right there. So what I did is, what if I make that 3 a 4? If I can make that 3 a 4, then this does look like at 4 times the absolute value of an A matrix times the absolute value of an X column vector. And that I saw that and I said, well, that'd be pretty nice. Then what I said is, I could think about a 1 norm for a vector. Like if I put the FLE1, FLE2, and FLE3, if I put those together as a vector, then I have the floating point representation of ax minus b, okay? And if I put it as a vector and then I do a 1 norm of that vector, then this floating point representation, the 1 norm of that vector, would be a simple sum of FLE1 absolute plus FLE2 absolute plus FLE3. So you just sum these 3 up, and that would be that left-hand side of this. And then if I were to do the same thing for my 1, 2, and 3, make that a column vector, and then do a 1 norm of that, and that would take the place here. So we would know that the 1 norm of this, because of this, you're just summing the sum, that's going to be less than or equal to the sum of these 3 absolute valued, or the 1 norm. So I had that, and then I said, going back to looking at this as matrix multiplication, I thought, what if I were to take the incoming A and instead of showing it bracketed, I've just switched to a bold because I want to emphasize that I'm taking that matrix and I'm taking the absolute values. So that is a matrix. That's a n by n, or in this case a 3 by 3. And I'm taking that as a matrix, just each element absolute valued. And then I'm taking the column vector x, absolute value, and doing a matrix multiplication, scaling the result by n plus 1. In this case, it'd be 4, because n's 3. And it just makes it a little bit more than what we had, because when I go and generalize this, you'll see that the scalars as the columns advance, the scalars diminish. So it's a little bit more, but I still think it's a nice look here. So it's going to be a little bit more than what we would have. But that's matrix times matrix multiplication scaled by a scalar. And then we add in, so that's results of a vector. And then we add in a vector that's absolute value of b, add those in, and then take a 1 norm of all of that. So that gives us a nice bound, not quite as tight as the bound, but still very nice. So I call that the Griffiths method. Is very easily calculated in MATLAB. You do absolute value of this, absolute value of that, multiply by that n plus 1, and then add in the absolute of the b, and then do the 1 norm of the result, multiply by machine epsilon. So I finagled this into a matrix form. Again, absolute values on the matrix and the vectors before you do the matrix multiply and the matrix vector addition, and then you do the 1 norm. Okay, so I think I've belabored that quite a bit there, but that's all it is. So before going into the Submultiplicative method, let's get a little bit of a consistent background on maybe absolute value first. So absolute value, as you know, operates on a real or complex number, and you'll get a real scalar result, and the real scalar result will be greater than or equal to 0, no matter what x you're choosing, whether it's complex or real, and it will be equal to 0 only when x is 0. And if you think about it, the product of x and y, absolute value, is going to be equal to the product of the absolute values. So that makes sense. Whether it's real or complex, that's true. And then there's this triangle inequality that I mentioned today. And what that says is x plus y absolute value is going to be less than or equal to the absolute value of x plus the absolute value of y. So triangle inequality is true for complex or real values. So take and notice how what I just showed you on absolute values for scalars, complex or real, is sort of looks like this norm for vector norms. So I'm going to define a norm function, which is the double bars now, double vertical bars. It operates on a complex or real vector, and that's going to come as either complex n-dimensional space or a real n-dimensional space. That's going to give you a real scalar result. And again, the double bars on the vector here, that's going to give me a real scalar result greater than or equal to 0 for any x in the vector space, and it's going to be equal to 0 only when the x is equal to the x vector or 0 vector. And if you take a scalar that is a complex or real value, and you scale that vector, then that's going to be equal to the absolute value of the scalar times the norm of the x. I haven't said whether this is a 1 norm, 2 norm, whatever. I haven't said. In fact, it should be true regardless, whichever norm you're doing. So that, okay? And then there's the triangle inequality thing that comes about again, and it says that the norm of the sum of two vectors is going to be less than or equal to the sum of the norms of the vectors taken individually. These properties that I'm showing you for vector norms, they are valid whether you're talking about a 1 norm, a 2 norm, or the infinity norm. So let's take it and extend it to matrix norm. So here, again, I'm showing the matrix as bold instead of bracketed. so that I can highlight that I've got the two vertical bars to denote the matrix norm. So if you could allow me to do the bold now for matrices, and I'm going to say, we're talking about a real or complex matrix, in this case A or D, and it's going to be n by n. So we're going to look at square matrices for now. And if I look at a norm of that, it's going to give me a real scalar result. And the norm of the matrix is always going to be greater than or equal to 0 for all matrices. It's going to be equal to 0 only when the matrix is equal to 0, the 0 matrix. And if I were to take us and scale the matrix by a scalar alpha, and that's going to be equal to the absolute value of that scalar, whether it's real or complex, times the norm of the matrix. And if I bring in my triangle inequality again, and I look at summing two matrices A and D, n by n each, then the norm of the sum is going to be less than or equal to the sum of the norms of the two matrices taken individually. Same thing again. So now for the new concept of submultiplicativity, let's say that the norm of the product of two matrices is less than or equal to the product of the norms of the matrices taken individually. So that is submultiplicativity. It doesn't always hold, but it does hold for the 1 norm, the 2 norm, and the infinity norm. Remember that the 1 norm is the max column sum norm, and the infinity norm is the max row sum norm, two important ones, and the 2 norm is related to the maximum eigenvalue of A transpose A. So, what is the submultiplicative method I've been talking about? So we're bringing in back in that beloved ax minus b, and what I'd like for you to do is kindly replicate this x vector, take that column and replicate it n times so that we create this n by n matrix x, okay? And do the same for the column vector b. Replicate it n times and we'll have an n by n b. It's just the columns are repeated in there. And from the definitions of max column sum norm, that's the 1 norm for the matrix, and also the definition of the 1 norm for vectors, you will see that the max column sum norm of matrix X, the 1 norm of matrix X, is equal to the 1 norm for the vector X. And similarly for matrix B that I've defined that way, the 1 norm for it will be equal to the 1 norm for the vector B. It has to be this way if you think about it. The columns of matrix X, it comes from the vector X, so that the 1 norm of this would have to be equal to the max column. So all of the columns would have the same sum based on how this is written out. So this has to be true, so that makes sense. Now, are you ready for this? I think that this is true, that this bound on what I'm looking for, the ax minus b, the 1 norm of that, is going to be equal to ax minus b, where I put in the matrix representations for the two vectors. See, these are going to be equal because I'm just replicating the columns there, so it's going to be equal to the 1 norm of that. And then I'm ready to bring in the supermultiplicative method here to say that this norm is going to be less than or equal to the 1 norm of matrix A times the 1 norm of matrix X plus the 1 norm of matrix B. And the last step is that I take the left-hand side and say that that's less than or equal to, where I substitute back in the 1 norm of the vector X and the 1 norm of the vector B. And then I get a very nice relation that says that a bound on the error, the one norm bound on the error, is going to be less than or equal to the one norm of matrix A, times the one norm of vector A plus the one norm of vector B. Very nice, very easily calculated in MATLAB. Norm times norm plus a norm. Very easily calculated. Remember, when this is true, it means that x is a solution to the equation ax equals b. So in summary, I've shown two error bounds for ax minus b that correspond with that very celebrated linear equation ax equals b. I've shown you my method, which is based on a floating point round off, and I did a little finagling or fudging to get it into a matrix form. And then I showed you the submultiplicative method, which is based on matrix and vector norms. It is very new for me, and I was really excited, eager to discuss it with you. I hope you enjoyed it.